What's going on, everyone? In this video, we're going to learn about the learnable parameters in a convolutional neural network. So let's get to it. Last time, we learned about learnable parameters in a fully connected network of dense layers. Now, we're going to talk about these parameters in the scenario when our network is a convolutional neural network, or CNN. We'll first start out by discussing what the learnable parameters within a convolutional neural network are. We'll then see how the total number of these parameters within a CNN is calculated. And after we see how this is done, we'll illustrate the calculation using a simple convolutional network. Alright, what are the learnable parameters in a CNN? Well, it turns out that generally they're the same parameters we saw in a standard fully connected network. That is, the weights and biases. But we have to consider how, architecturally, the two types of networks are different, and how that's going to affect our calculation. Let's explore that now. So, just as with a standard network, with a CNN, we'll calculate the number of parameters per layer, and then we'll sum up the parameters in each layer to get the total amount of learnable parameters within the entire network. For a dense layer, this is what we determined would tell us the number of learnable parameters. Now let's consider what a convolutional layer has that a dense layer doesn't. A convolutional layer has filters, also known as kernels. And as the architects of our network, we determine how many filters are in a convolutional layer, as well as how large these filters are. We need to consider these things in our calculation. With this in mind, we'll modify our formula for determining the number of learnable parameters in a convolutional layer. So, what is the input going to be for a given convolutional layer? Well, that's going to depend on what type of layer the previous layer was. If the previous layer was a dense layer, then the input to the conv layer is just the number of nodes in that previous dense layer. However, if the previous layer was a convolutional layer, then the input will be the number of filters from that previous convolutional layer. Now, what's the output? With a dense layer, it was just the number of nodes. With a convolutional layer, the output will be the number of filters times the size of the filters. We'll see this illustrated in just a sec. And for the number of biases, well, that's just equal to the number of filters in the layer. So overall, we have the same general setup of the number of learnable parameters in the layer being calculated as the number of inputs times the number of outputs plus the number of biases. Just with a convolutional layer, the inputs and outputs themselves are considering the number of filters and the size of those filters. Let's check ourselves by seeing this calculation in action with a simple CNN. Suppose we have a CNN made up of an input layer, two hidden convolutional layers, and a dense output layer. Our input layer is made up of input data from images of size 20 by 20 by 3, where 20 by 20 specifies the width and height of the images, and 3 specifies the number of channels. 3 channels indicates that our images are in RGB color scale, and these 3 channels will represent the input features in this layer. Our first convolutional layer is made up of 2 filters of size 3 by 3. Our second convolutional layer is made up of 3 filters of size 3 by 3. And our output layer is a dense layer with 2 nodes. We'll assume that the network contains bias terms and that we're using zero padding throughout the network to maintain the dimensions of the images. Check the zero padding video if you're unfamiliar with this concept. Now, the same rule applies here for the input layer that we talked about last time, where the input layer has no learnable parameters since it just contains the input data. So moving on to the first hidden convolutional layer, how many inputs do we have? 3 from our input layer. How many outputs? Well, let's see. Remember, the number of outputs is just the number of filters times the filter size. So we have 2 filters, each of size 3 by 3. So 2 times 3 times 3 is 18. Multiplying our 3 inputs by our 18 outputs, we have 54 weights. Now, how many biases? Just 2, since the number of biases is equal to the number of filters. So adding 2 to 54, that gives us 56 total learnable parameters in this layer. Now let's move to our next convolutional layer. How many inputs are coming into this layer? 2 from the number of filters in the previous layer. How many outputs? Well, we have 3 filters, again of size 3 by 3, so that's 3 times 3 times 3, so 27 outputs. Multiplying our 2 inputs by the 27 outputs, we have 54 weights in this layer. Adding 3 bias terms from the 3 filters, we have 57 learnable parameters within the layer. Onto the output layer. How many inputs? We may think just 3, right? Since that's the number of filters in this last convolutional layer. But that's not quite right. If you followed the Keras playlist, then you know that before passing output from a convolutional layer to a dense layer, that we have to flatten the output by multiplying the dimensions of the data from the conv layer by the number of filters in that layer. In our case, the data is image data. Since we're assuming that this network uses 0 padding, the dimensions of our images of size 20 by 20 haven't changed by the time we get to this layer. So multiplying 20 by 20 by the 3 filters gives us a total of 1200 inputs coming into our output layer. Now, since this output layer is just a dense layer, the number of outputs is just equal to the number of nodes within the layer. So we have 2 outputs. Multiplying the 1200 inputs by 2 outputs, that gives us 2400 weights. Adding in our 2 biases from this layer, we have 2402 learnable parameters here. Summing up the parameters from all the layers gives us a total of 2,515 learnable parameters within the entire network. So we can see that the process for determining the number of learnable parameters in a CNN is generally the same as a standard fully connected network. But we have to do a little extra work by considering some things like the number of channels being used in an image data, the number of filters, the filter sizes, and flattening convolutional output. We'll be implementing this in code using Keras in the next video, so stay tuned for that, and in the meantime, let me know your thoughts in the comments. See you soon.